So we left the last video with a close look at the standard deviation of the mean. And what we left with is that if you go do an experiment yourself and you report your average, and you report your average with the uncertainty of plus or minus the standard deviation of the mean or the standard error, then you're getting really close as you can, say, to this thing in science here, which I guess is kind of elusive. What's called the truth, I guess, or statistical truth. But if you write this for an experiment, then there is a 68% chance that the actual result, the real actual correct result, is in this range. And so that's pretty good. And so that's about the best you can do with random errors. And again, all of this that I have on the screen at the moment here assumes that all systematic errors are in check, and we're just dealing with random errors at the moment here. So in other words, there's no bias in voltmeters, and you're sure the thing is zeroed properly, and you're reading your yardstick properly, and like you yourself aren't constantly doing something wrong when you take a measurement. This is about as close as you can get to the truth of the thing. So I'd like to just end this video here. This will be a short one here. It's a bit of reading out of your book. This comes from your book on Taylor here in page 103. And he has sort of some nice passages in here I'd like to share with you here. Let's just read it then. So he says here that an important feature of the standard deviation of the mean, with that very simple definition here, is the factor square root in the denominator. So the standard deviation represents the average uncertainty in the individual measurements. Thus, if we're able to make some more measurements using the same technique, the standard deviation would not change appreciably. Okay, that's an important point here about this. The standard deviation would not change appreciably. So it sort of tells you then that once you develop a measurement technique in an experiment, you have all the systematic errors in check, then basically this standard deviation becomes kind of fixed for you. And there's not a lot you can do about it insofar as random errors only. Okay? There's not a lot you can do about it. It's sort of just something that is endowed on every measurement you make. If it's just random errors, then your technique and everything you're doing will just have some standard deviation that just won't change very much, even if you take more and more data points. Remember, another data point comes in. The only thing you can say for sure is that when you take that data point, there's a 68% chance it'll be within the range of X bar, your average, plus or minus that standard deviation. You're just sort of bound to that. Okay? Onwards. On the other hand, the standard deviation of the mean would slowly decrease as we increase n. This decrease is just what we would expect. If you make more measurements before computing an average, we would naturally expect the final result to be more reliable, and this improved reliability is just what the denominator guarantees. This conclusion provides one obvious way to improve the precision of our measurements. Now, I'm being very careful around here. I shouldn't have even said that word. In fact, I'm just going to cross it out. But okay, it's in there nonetheless. Okay? And so this is a very, very important paragraph here to allow you to contrast just the standard deviation and standard deviation of the mean here. Because the standard deviation, as he says here, is more or less fixed once you get going on taking your data. There's not a lot you can do about it here. But remember, this is proportional to 1 over the square root of the n. So if you take more and more data points, this will shrink. And we're also remembering that our final result is not reported like this. Okay, we're not going to report a result with this fixed quantity, the standard deviation. We don't really do that. It's going to be the average plus or minus the standard deviation of the mean. And so you see, we are in control then of, if we have the economics and the wherewithal to take more and more and more data points, we can shrink that result. And of course, we have the interpretation of all this in the past video here. But again, the 68% pops up, but 68% of actual result in this range. So the meaning of it changes just by dividing by that square root of n. There's a 68% chance that the actual result that you're looking for will be in this range. And so that's the interpretation of the standard deviation of the mean. The standard deviation of the mean, in my opinion, gets more at the matter of truth in measurements. You know, what actual value am I going for? Where the standard deviation just sort of tells you how individual data points are fluctuating. Okay? And lastly then, just to conclude with our reading here, unfortunately the factor of square root n grows rather slowly as we increase n. So for example, if we wish to improve our precision by a factor of 10, simply by increasing the number of measurements, we'll have to increase n by a factor of 100, which sort of is a daunting prospect. Okay? And then once again, I'm going to cross out this word here, okay? But it is not unreasonable in some quantum lab experiments, if you really wanted to go for some really nice result, just to take a lot of data. Like we could have just really decided with some systematic way of going in the lab and just dropping the ball into the sand to get cratering. We could have just done that hundreds of times. Maybe we would have agreed to meet for 2 hours every day and just get a bunch of measurements like that. But that's not always the case. I call it the economy of doing experiments. It's not always economical to do these measurements here. So again, we are also assuming that we are neglecting these systematic errors because these are not reduced by increasing the number of measurements. So if you're just doing something wrong every time, either you're doing something wrong or your meter is doing something wrong, there's some offset or bias in there, then that will not go down as you take more measurements because it's always in the measurements, right? That's in practice if you want to increase your precision. Oh my gosh, take that word out again. Appreciably, you will probably do better, improve your technique than to merely take more measurements. So if you're having some trouble with something, you might re-examine how you're taking your data. That is improving your technique instead of just taking more measurements, say with a technique that isn't so polished. Okay, so in the next video then, I'm going to show you some computer graphics of what all this means.